working. Hello, I'm James Wootton. I'm a person who doesn't get on very well with mics, so if there's anything wrong with this mic, let me know. I'm also from IBM Research in Zurich, and I work on quantum computing, and I work on our open source project called Qiskit for doing quantum computing. So in this session, I'll take you through some very basics of quantum computing and Qiskit, and it's a workshop, so you can run code along with me. There's free plans for how you could do this. The repository you can find at the other end of this shortened link. So go there and you'll get to this repository. Obviously, you can see the URL at the top as well. So yeah, you can download or you can clone this repository, and it has some Jupyter notebooks in that you can that I'll be using as a basis for this presentation. So if you have the ability to use Jupyter notebooks and you have Python free, then all is well with the world. There are a few packages you need. Mostly it's like NumPy but there's also matplotlib, which for me is very normal, but maybe not everybody uses it. Plan B is we have this cloud service that you can use, and it hosts Jupyter notebooks, and then everything is already installed there. It's a nice environment where everything is already set up. Obviously it needs the internet, and so that's why it's not Plan A, because it doesn't go without its hitches. Also, not absolutely everything that I'm going to be presenting is able to run on that cloud service. But Plan C is not to run anything. You can just sit and watch and learn about stuff, and then go on to do things later. Okay, so what I'm first going to do is give a little bit of an introduction to what quantum computing is, and do so with fancy pictures and buzzwords, just to motivate what this is all about. And at the bottom there, which hopefully people can see the bottom, is this shortened link to the repository. So at any point you can always go and have a look at that. Yeah, I'll go through this while you try Plan A and Plan B and resign yourselves to Plan C, and then we'll see what's going on at the end. Okay, so the first thing to note is, quantum computing has the word quantum in it, and if you watch films, then, for me, sci-fi films often seem like fantasy films, except you replace the word magic with quantum, and that doesn't really help quantum computing, because we're an actual technology able to do stuff, but people have this misconception that it's somehow strange or chaotic or unpredictable. So it's not. It's a science, and we can use it for things. And the motivation behind quantum computing, and this is something that has been known since the 80s, is that there are some problems that are just too hard for current computers. And a classic example of this is simulating quantum systems. If you have a relatively large system, like a molecule, then the amount of memory it takes to store the possible states for a large quantum system is huge. And then the number of operations you'd have to perform in order to simulate a large quantum system is also huge. So you get to the point where you have the kind of molecules that you might be interested in from the perspective of drug design or creating fuels, or trying to understand how plants create fertilizers so much more efficiently than we do. And these are just too hard to run in the lifespan of a human, even if you run it on a fancy supercomputer. So this is a caffeine molecule. It's very hard for us to know how caffeine does what it does, because it's too big, but somehow it does what it does. And probably all of you are living proof of that. It doesn't need to run a program on a supercomputer to tell it what to do. It just does it. So quantum systems are good at knowing what quantum systems can do. And so if we want to know what a molecule can do, well, the most naive approach might be you might think you just get that molecule and look at it. And then if you want to know what happens if you prod it in a certain way, then you prod it, and then you see what happens. But trapping and dissecting a molecule is not like dissecting a frog. It's a much smaller and harder to reach scale. So instead what we can do is make quantum systems that are easy to put information in, to read information out, and to manipulate. So specifically quantum systems that we want to manipulate, and then we can use those to simulate other kinds of quantum systems. So we do this using little loops of superconductors, and they're so small that you can induce quantum effects on them, and you can control them via microwave pulses. So this is a well-controlled quantum system that we can use to do quantum simulation. But a very important point is something we've known since the 90s, is that there are other kinds of problems that you can do on a quantum computer. So quantum computers are universal. You can compile any computation onto a quantum computer. I would advise that you don't. If you want to play Mario Kart, quantum computers are not the place to do that. If you want to add numbers, then use a normal computer. Quantum computers are not going to give you any advantages in things like adding numbers. But there are various problems, such with one of the most famous being factoring. So if I have a number and I want to know what prime numbers I need to multiply together to get that number, this is something where the computational effort you have to put into that increases exponentially with the number of digits in the number, until you get to a point where numbers are so big that you just cannot conceivably factor that number on any device that exists in the lifetime of a human. And that principle is actually used behind a lot of cryptography, that it's essentially impossible to factor numbers, and therefore we can use this as part of cryptography. Although quantum computers, there is an algorithm that can factor things much more efficiently than that. So things like factoring, but also optimization algorithms, graph theoretic problems, all kinds of problems that are of use in all kinds of areas can be done on a quantum computer. So I see it like a graphics card. You know, you don't run everything on a graphics card, but some things are better on a graphics card. So you have the ability to target a graphics card when you're running a certain operation, when you're running a certain problem. It's going to be like this with quantum computers. It's not going to replace your normal computers, but sometimes as part of whatever use case you have, you need to solve a certain problem, and it's easier just to send that out on the cloud to a quantum computer than it would be to do it on a non-quantum device. So we have an open source framework now to do quantum computing, to set up jobs, to send those jobs, to get the results. It's called Qiskit. There are others also available. So there are a few of these available now. All but one of them are based in Python. So Python seems to be taking off as the language of choice for quantum computing. But the most important one is Qiskit, which is the one which was founded by IBM and which is mostly developed by IBM, although we also have a lot of external contributors. So far I've told you how great quantum computing is, but it is very much a technology that's on a journey. In the 80s, people first started to come up with the idea of it. So in 1981, the first conference on physics of computation co-hosted by MIT and IBM was kind of when quantum computing was born, and IBM was even involved all the way back then. And this is a very IBM-centric timeline, so almost every other milestone is IBM. Other perspectives might write different timelines, but the company has been involved quite a lot over the last few decades. So we've got to a point now where we have prototype hardware that's on the cloud. So it's in the hands of everyone, but it's not yet. I would normally say I've got to adapt to the new era now. I was going to say it's not yet possible to do anything that a normal computer can't do. But a certain company have done some certain results that have been leaked recently that may challenge that view. But you can't do anything useful on a quantum computer that you can't do otherwise. We haven't yet reached that goal, which is, I would say, the more important one. But we're very much at a point when you can start actually using the technology to do stuff. So what kind of stuff? Well, one thing is to plan for your future use cases. You can look at there's something called the Quantum Algorithm Zoo. You can look at this, and you can, that link shouldn't be there. You can look at this, you can look at the Quantum Algorithm Zoo, and you can see the kind of things that are sped up by a quantum computer, and you can try and work out how that might impact you in the future, and maybe look at proof of principle applications you can do to prepare yourself for that. So we would say that a revolution is coming in, say, about 10 years in terms of the usefulness of technology, and you should probably start preparing for that now. The cryptography is one case where it's going to be significantly disrupted by quantum computing, and they have already been preparing for a while, but also everyone else can get going. So, for example, some of my colleagues at IBM Research in Zurich have done some proof of principle results for quantum risk analysis, so improving risk analysis using quantum computation. But probably the most important use over the next few years is that it will be a platform for science. That's actually how I came to use IBM's technology. Before I joined IBM, I had an experiment that I wanted to do, and convincing experimental physics groups to do your experiment is very hard, but then IBM just put it on the cloud, and I could do my experiment in an afternoon, which was quite revolutionary. So there's a lot of people that have been using this for science. So if you have a scientific background in the field, then it's kind of obvious what you might do. If not, you can still have a go at the science. I like to liken this to the controls of CERN being put on the internet for anyone to fiddle around with. This is similarly one of the most advanced pieces of experimental physics equipment in the world, and yet you can just log into a website and drag and drop some things and press run and run something on a device which is sitting at one of the coldest points in the universe, which is pretty cool. And I'm plugging our awards throughout these next few slides. So for all of the things that we like and we're trying to encourage, we have some awards that we've just announced. So for people who do those things, they can submit their work to the awards. So there's a Best Paper Award if you are doing science. Another thing is it's a platform for education. So this is also something which is also one of the use cases for Python. Python is this easy programming language, so it's great for teaching people about programming. Well, quantum computing brings quantum physics to a point where people can easily manipulate it and use it and get hands-on with it. So quantum computing in the next few years will be a great platform for education, and we have various awards for that. We also have a textbook, and I'll be taking you through some of that textbook today. And it's also an open source project, so if you're looking for an open source project to spend your precious time on, then Qiskit is one of them. So we have an award where you could specifically do a certain optimization problem which is suitable for people who don't have a quantum background. But we're on GitHub, and there's good first issues, and there's plenty of ways to get involved, and there's plenty of people who haven't got a quantum background that have started contributing to this project. And also you can just have some fun. So if you're a hobbyist programmer, then you might be always on the lookout for something new and fun to have a go with, and you can try out quantum computing. So this is kind of the way I do things with quantum computing a lot as well. I look at how quantum computing and games might intersect. So this is an example of a procedural generation project that I've done using Qiskit. And if you make a quantum game, then there's an award for that as well. So that is the basics of why quantum computing exists. And now we can switch over to this again. So now I'm going to go through some Jupyter notebooks. So a quick show of hands, who's got Plan A working? Wow. So this is definitely a Pythonic audience. I've tried this before with less Pythonic audiences. Yeah. And who's on Plan B? Wow, your sign-ups are great for our metric, so thank you. And then Plan C? Okay, fair enough. So is there any specific issues that people want to ask me who are in the boat of Plan C, or to get themselves out of it, or are you happy? Yep. Okay, so the first thing I'm going to do is we have a textbook. One of our first sections is Introduction to Python, and I'm sure you'll hate that section because you'll think this is not how you should introduce people to Python. What the hell kind of syntax is that? So we're not going to do that. Then there's also one that's an introduction to Qiskit, but I'm going to do that via this one at the moment. So this is called The Atoms of Computation. And really, sometimes programmers ask me, how does quantum computing differ from normal computing? And I think one of the main differences is you have to start thinking at the machine code level. So if someone asks you what's kind of the simplest thing you can do in programming, you might say, well, print hello world, or add a couple of numbers. But those are quite complicated things. Adding numbers, you've got to represent a number as a bit string, and then another number as another bit string, and then you've got to do all these bitwise operations between them to generate another number. My God. And the number of bits you need for hello world, even worse. So you have to kind of change your perspective a bit and come down to the machine code level. So that means, I'm going to import some stuff here. Come on. So that means getting to the level of circuit diagrams. So who here looks at that and knows what's going on? Not many people. So yeah, circuit diagrams is definitely somewhere to start. So this is a way you can express computation in a very simple form, in that you have these lines along which bits travel, and then they go into these gates, and these gates are operations. So gates are kind of like a function. This is a function that takes 2 bits as input and gives 1 bit as an output. And this is an alternative kind of function that does the same thing. And so this is a computation. Well, this is a whole thing that takes 2 bits as an input, A and B, and then gives 2 bits as an output, S and C, and then that's your computation. So this is a certain type of adding that's going. This is the way you can add 2 single-bit numbers to get 1 2-bit number. So 0, 0, 0 add 0 will come out as 0, 0. 0 add 1, or 1 add 0 would come out as 0, 1, and 1 add 1 would come out as hang on, how does adding work again? Well, we'll do it throughout. So if you know what this looks like, then this is the kind of language you'll be taking with quantum computing. But this is the classical version. This is what's happening in your normal computers. These things here, these are what transistors do. Okay, so I've imported my stuff. That's always good. Now, the very heart of quantum computing is the quantum circuit. And so it's kind of the quantum version of this. So for this, you might, if you were to make a Python object, and in fact, I'm sure there are Python packages based around doing circuits. But if you were to make if you wanted to make a Python object which contained this sort of structure, then you might declare it in terms of the number of inputs it has and the number of outputs it has, and then you'll have some methods that you can use to stick these gates in there. They're called gates, and hook them up. So this is basically what we need in our quantum computing. So we're thinking at the machine code level. That means thinking at the level of bits. So in the classical circuit, we might say how many bits we want as input, how many bits we want as output. In quantum computing, our basic fundamental unit is called the qubit, the quantum bit, and we'll look into what they are over the course of this. And this is what we build out of some sort of physics. At IBM, we build them out of superconductors. There are also other approaches. So when we define this fundamental object, we have to say how many qubits we want in it. But also a qubit is this weird quantum thing. At the end, we want a proper output that we can read as non-quantum animals. And so at the end, we get an output which is bits. So when we set up a circuit, we tell it how many qubits we want and how many bits of output we want to get out at the end. So we define the number of qubits, we define the number of bits, and then we define our quantum circuit object using the number of qubits and the number of bits. So over here I did from Qiskit import star, which is why it took so long. So this quantum circuit object is something that I imported from here. So from Qiskit import quantum circuit is what was going on there. So now I've got a quantum circuit. I can execute this. And if I already use the draw method of the quantum circuit to show us what's happening in that quantum circuit, I get this. Not much is happening. We haven't added anything to this circuit yet. So what we can do is add in some quantum gates. So these are the basic operations. So let's add in something called X, and we've got 2 qubits in this particular example, and those 2 qubits, we number qubits from 0, so they're called 0 and 1. If we had 3 qubits, they would be called 0, 1, and 2, and so on and so forth. So it's a little bit of a confusing case, actually, having 2 qubits, because they're called 0 and 1, but they're also kind of like bits, which are 0 and 1, but they're not the same 0 and 1. So let's do an X on qubit 1. Did we already do that, actually? Anyway. So we add these gates in, but one thing that's very important is at the end of a circuit, we have to actually remember to extract the output. So what that means is that we use this measure command, and we have 2 arguments to that. One is the qubit that we are extracting the output from, and one is the bit where we are putting the output. So we have this register of bits where we place an output, but we also have some qubits from which we extract an output. So here, I'm just saying I want qubit 0 to give me an output, and I want to put that output on bit 0, and then I want qubit 1 to give me an output, and then I want to put that output on bit 1. So when we do this, then this is what we get as our circuit diagram, as our visual depiction of what's going on in this fundamental element of a quantum process. So here we've got this qubit 1, it's straight away taking an output. So qubit 0, is straight away getting an output extracted from it. Qubit 1 is having this X applied to it, and then an output is being extracted. So what does that mean? Well, of course we'll go through some of this in more detail, but let's get to the point where we actually run a circuit. So in Qiskit, to run a circuit, you have to first decide where you're going to run it. So you set up a back-end object. So we have different ways to set up a back-end object, but this air is where all of our simulators live. Because you can either simulate it on your actual device, because if your circuit isn't composed of many qubits, you can simulate it quite easily. If it's composed of more qubits, then it will take more time. It will take an exponential amount of time with the number of qubits you have. But for something like this, a 2-qubit circuit, it's very easily to simulate. So this is the local simulator, the easiest way to simulate things. And then we run it using the execute command. So we tell the execute command what circuit we want to run, where we want to run it, and typically we run it for many repetitions to get some statistics out. And then stuff happens in Qiskit. execute gives you a job object. From the job object, you run the result method to get a results object, and from the results object, you run the method to get the exact kind of results that you want, which if you're running it all on the simulator, then you can just kind of combine it all into one line and forget about all that crazy shit. So the typical way to get results is this thing called a counts dictionary. And the counts dictionary is basically a histogram in the form of a Python dictionary. I'm just going to zoom in a bit. So it tells you the result you get out and the number of times you get that particular result. So how do we interpret this result? Well, it's giving us a bit string. So we have 2 qubits. We have a circuit with 2 qubits and 2 bits as output. So that is, because we've got 2 bits as output, is giving us as output a 2-bit string. So that is what we're getting here. This is the output from our quantum computation. It is a 2-bit string. And we ran it 1,000 times, and every one of those 1,000 times it gave us the same 2-bit string. So we've got a pretty boring circuit here which always gives us the same output. And why did it give us that particular output? Well, let's run it again, but let's this time not include any gates. So this time we are initializing 2 qubits and straight away extracting an output from them. If we do this, then we always get the result 0, 0. So what this is telling us is that a qubit is always initialized in such a way that it gives us the output 0. So if we initialize a qubit and straight away say, give me an output, it will give me an output 0. And we've got 2 qubits, and so they're both giving us 0. And what this X gate is doing is it's flipping one of those bits from 0 to 1. So now instead of getting 0, 0, we get 1, 0, because this bit is flipped from 0 to 1. Now, herein lies one of the most annoying pieces of Qiskit, so concentrate. If you were to take that string and ask, say, for the first or the element 0 of this string, what element would it give you? It would give you the 1. So the element of this string labeled 0 here is 1. But where did we do the X? We did the X on the qubit labeled 1, and the output from the qubit labeled 1 was put on the bit that Qiskit labels 1. So the bit that Qiskit labels 1 is placed in the string where Python labels that element 0. Basically, it's the wrong way round. Let's call it what it is. It's the wrong way round. So if we added some more in here, for example, just to make it so that we've got more than just 2, it's flipping this qubit 1, it's flipping output, the output bit 1, and so this is, if we asked what is the output bit 1 of this, it wouldn't give us that 1, it would give us a 0, so we have to go to 2 to get that 1. So it's basically, it labels the bits the other way around. So yeah, just be aware of that. If you ever get confused with where your outputs have gone, then remember that I told you that something weird is happening, and you'll find them. So also we have this H gate in here on qubit 0. So let's see what that does. Okay, well, I didn't reinitialize the object, so let's do it again. Once we use this H gate, then we start seeing some randomness. So we did it on qubit 0, which we output to the bit 0, and here we see that half the time it comes out 0 and half of the time it comes out 1. So at this point, this H gate just seems like a coin flip. It adds in some randomness. But it's not just randomness, it's more nuanced than that, as we'll see later. So yeah, this is one particular way of getting results as effectively a histogram in a dictionary form. Another way to get results is to use, instead of get counts here, to use get memory. And you also need the keyword memory equals true, just to make things complicated. And then this will give us a list, an ordered list of the results. So we'll run it the first time, and then it will see what the output is, and it will give us that, and it will run it a second time, and so on. So if we just want a single output, we can just do one. We can ask for the first element of that list, and you will just get a single output every time. And as you can see, because of the randomness, it changes randomly. Okay, so let's do something with this. So I'm going to show you how to make a 2-bit adder with Qiskit. So this is a 2-bit adder made with normal computing. I'm going to show you the equivalent in Qiskit. So just to motivate a 2-bit adder, I'll remind you how to add. So I'll take you back to your primary school days. I won't take too long about it because I'm sure you remember. But just so we're all on the same page with the terminology I'm using. So for example, let's talk about a number, 9,213. So when we write down 9,213, we write a 9, then a 2, then a 1, then a 3. And why do we do that? Well, it's because we are saying that it's 9,000 plus 200 plus 10 plus 3. But why do we do that? Well, it's because we are used to expressing numbers in terms of powers of 10. So 10 to the 3 is 1,000, so we're saying how many 10 to the 3s we have. 10 to the 2 is 100, so then we're saying how many 10 to the 2s we have. And then we say how many 10 to the 1s we have. And then we say how many 10 to the 0s we have. And so on. So we're expressing a number in terms of its powers of 10. But we could equivalently express a number in terms of its powers of whatever. And in binary, we of course use powers of 2. So 9,213 could be expressed as 1 10 to the 13, 0 10 to the 12, 0 10 to the 11, 0 10 to the 10s, 1 10 to the 9, and so on and so forth, which means that the binary representation of this number is 1 0 0. Well, no one benefits from me reading that out, does it? And this is actually why Qiskit numbers things the way they do, because so if you asked Python about the 0th element of this string, it would give you the one on this end, but it's actually the one on this end which corresponds to 2 to the 0, and then this one corresponds to 2 to the 1. So this is where the Qiskit numbering of the bit strings comes from. It's not the Qiskit numbering, it's, well, okay, maybe this is the right numbering and Python's got it wrong. But it's certainly annoying that they're the different way around sometimes anyway. So of course binary strings can be used to represent more than just numbers. They can be used to represent everything, and then also any computation is basically the manipulation of binary strings, and you can represent all computation as in terms of fundamental elements that just take 2 bits and output a single bit. So once you have that element, then you have everything. So a universal logic gate is the NAND gate. So this is just a way of taking 2 bits as input and giving 1 bit as output, and everything can be compiled down to NAND gates. And there's even a course called NAND to Tetris, which takes you from just NAND gates to building your own operating system to implementing games in that. So if you think NAND gates sound fun, and then who wouldn't? Then you can have a look at that. Okay, so let's just look at some binary strings in Qiskit. So now we're going to do some bit strings with 8 bits. We're going to set these up in Qiskit. So here's where I'm going to say how many bits there are, and then I'm going to initialize a quantum circuit which has n qubits and n output bits. Often when people initialize quantum circuits, then they do just use as many qubits as they do output bits. But in general, in quantum computing, these numbers can be different. but it'll always be the same in what we do today. And then I want to extract an output from each of those qubits, so I have to loop over all of my qubits and add one of these measure operations. I should maybe point out, why do we have to have this measure operation? Well, in quantum systems, which is what qubits are, well, how to say it without sounding like a pop science article? Quantum systems change when you observe them. So a measure is not a passive act. You're not just having a little glimpse at what it's doing and then it continues to do what it did forevermore. When you measure something, you are coupling yourself to it, and you are changing its behavior from evermore. So the moment at which you extract an output is an important moment in the life of a qubit. And that's why we have to have explicitly these measure operations, which is where the qubit sends a message down into our normal classical world. And that's why they're represented in this way. So this is meant to be a very simple representation of kind of like a needle on a measuring device. That's where the symbol comes from, and then it's sending a message down into our normal everyday world. I should zoom out a little bit now. So this is what's happening now. I get 8 qubits, and I immediately extract an output from all of them, and then I want to look at what that output is. So if I go down here, what I'm going to do is visualize this. I'm visualizing the counts as a histogram. So if I just put counts in here, then it would be one of these dictionaries, if I move that up, which is the bit string we get out and then the number of times it came out. But we can use one of the tools from Qiskit just to make that into a histogram, because everyone loves histograms, right? This talk is on the PyData stream, so you can't say you don't love histograms. So basically we're getting 0, 0, 0, 0, well, 8 zeros out all of the time. And this is because, as I said earlier, a qubit by default outputs 0. When you initialize a qubit, it always outputs 0. And we're not doing anything to these qubits, we're just extracting an output, so they're all outputting a 0. Now, if we wanted to do something more exciting, then we could put a gate in. So here I'm putting an X gate. So here I'm doing something slightly fancy. So let's look at exactly what I'm doing. I'm setting up a quantum circuit here, and I'm calling it QC encode. And if you look at how I'm initializing that quantum circuit, I'm initializing it with only one argument. So I'm saying here is a quantum circuit which has n qubits. How many outputs does it have? I don't know. I'm not including the prospect of extracting an output from this circuit, which is a bit weird, but you'll see how. So, okay, it has no output, so it's completely cut off from us, but we'll see how we get around that later. So now I'm putting a gate into this, and this is this X gate, which is effectively a NOT gate. It just flips a 0 to a 1. So on qubit 7, I'm flipping that 0 into a 1. Now, how do I see that I've done that? Well, actually, if you look up here, I called this QC output, and I'm basically, and this is just consisting of measures. This is just consisting of operations which extract an output from a quantum circuit. So I'm going to use this to extract outputs from the next few circuits. So basically I'm going to take this where I do something actually interesting. I do a gate, and I'm going to add it onto this, which is where I extract outputs, and it's going to allow me to get an output at the end. So I make a circuit which is me adding my encoding circuit, which is where I did the gate, with my output circuit, which is where I'm taking these measurements, where I'm doing these measurements. And the resulting circuit just takes the first circuit I made and then adds on the second circuit. So there was the same number of qubits in both of these circuits, so it's very well defined what happens when this when I add, I just basically take one of these circuits and the other one and put them next to each other. There are many other cases where you can add circuits to do different kinds of effects, but I won't go through all of those. This is just the kind of syntax I'm going to be using here. And now if we run this combined circuit, then we get a result that to me is unexpected. Because I haven't executed this cell yet, so it's still remembering a QC from earlier. So here, always I get out the output 1 and then 7 zeros, just because I flipped one of these bits from 0 to 1, and the rest of them remain 0. So with this, I can encode a number, and in this case, I've encoded the number which is 2 to the 7. And then I can, if I choose to, I can encode other numbers. So if you want to know how old I was when I created this notebook, I was that old. So actually, where have I gone? So then if you add the output circuit to this, you can extract the actual output and you'll get the bit string, which in this case will be 0, 1, 0, 0, 0, 1, 0, 0. Okay, so this is just me encoding binary strings in Qiskit. We have not really gone anywhere quantum yet, or done anything, well, yeah, let's say it, done anything interesting. So, but is everyone fine with how I'm encoding bit strings using qubits for no apparent reason? Now we can get on to actually doing something. So as I said earlier, if you want to add, there's no better computational device to add on than the ones we already have available to us. But let's look, adding is a very simple algorithm. So if we're trying to look at how to actually do something with quantum computing, then seeing how to add is kind of like a very simple hello world. And then from that we can go on to do more complicated stuff. So how does one add? Well, at primary school, what I was taught to do at least was to write the numbers that I was adding, one on top of the other, and then you can go down through the columns. 3 plus 4 is 7, 1 plus 5 is 6, 2 plus 8 is 10, which means I put a 0 down here and I carried a 1, and then so on and so forth. So this process of adding two numbers of arbitrary length is compiled down to adding just single-digit numbers. Mostly we just add 2 single-digit numbers at a time, but in the case of a carry, we add 3 single-digit numbers, because here I have to do 9 plus 1, but also carry the 1. So if we have the ability to add at most 3 single-digit numbers, then we have the ability to add anything. And if we have the ability to add 2 single-digit numbers, we can also use that to add 3 single-digit numbers. So this operation of adding 2 single-digit numbers is kind of the most fundamental aspect of addition. If we have the ability to do that, then we can take whatever we've used to do that and wire it up many times to make something that can add anything. Now, how does this look in binary? Well, you just do the same thing, but in binary. So 1 add 0 is 1, 0 add 1 is 1, 1 add 1 is 2, and 2 is 1, 0. So in the case that we have 1 add 1 is 2, we have to express this as 1, 0 and carry the 1, and then we have 1 add 1 adds 1 is 1, 1, and so on and so forth. So the important thing to note about this is that there's basically only, once we get it into binary, it becomes a lot simpler. That if you want to add 2 single-digit numbers, which is the fundamental process of addition, there's only 4 cases you have to be able to fulfill. So if you can make some sort of device, be it made out of transistors or the flow of water through a channel or whatever, if you can make some sort of device which can encode and perform this operation, then you can build any adder you want. And so what it has to do is, for the case of 0 plus 0, it has to give you 0, 0. For the case of 0 plus 1, it has to give you 0, 1. For the case of 1 plus 0, it has to also give you 0, 1, because this is 1 in binary expressed as a 2-bit string. And in the case of 1 plus 1, it has to give you 1, 0, because this is 2 in binary. So this is a half adder, and what we saw at the top was a half adder using Boolean logic gates, which is basically what happens inside these devices. What we're going to do is implement a half adder in Qiskit. So the way we're going to do this is using a circuit which looks something like this. So we're going to have 4 qubits in this circuit. We're going to have 2 output bits. So this is actually an exception to the rule I said earlier. And so what we're going to do is we're going to use 2 of these circuits to encode our input. We're going to do 2 of these qubits to encode our input. We're going to use the other 2 qubits to extract our output. And then in the middle, magic's going to happen. So why don't we just use 2 qubits? And the reason is that quantum computations always have to be reversible, which means that, so if you think of normal reversible operations, means that whatever bit string, whatever input you give, has to lead to a unique output, such that it is possible in principle, given an output, to infer exactly what the input was. Now with adding, this is not reversible in itself, because 0 plus 1 and 1 plus 0, these are 2 separate inputs, but they both lead to the same output. So if you do this with a reversible computation, you need somewhere where you're scribbling notes throughout the process. So this is why we need more qubits than there are bits in the problem. We just need an extra little bit of space to ensure reversibility. So we're going to encode our 2 input bits, and we encode these 2 input bits using X gates. So if we want 0 plus 0, then we have nothing over on the left-hand side there, so that they just go in their natural 0 states. If we want 0 plus 1, we put an X on one of those to flip it to a 1, but leave the other one 0. And if we want 1 plus 1, we put an X on both, which is what we've depicted here. And then at the end, we extract outputs. So what do we need to put in the middle? Well, let's look again at what our half adder does. In the case, so if we look at the output we need to get from a half adder, then if we look on the left-hand side of, okay, let's look first actually on the right-hand side of these bit strings. In 2 cases, we get a 0, and in 2 cases, we get a 1. The 2 cases where we get a 0 on the left-hand side are 0 plus 0 and 1 plus 1. So they're the 2 cases where you add the same thing. You're adding 0 to 0 or 1 to 1. And the 2 cases where we get a 1 are 0 plus 1 and 1 plus 0. So that bit is basically telling us whether our 2 input bits are the same or different. So that is a piece of information that is telling us. So we need 2 components to making a half adder. One is to work out whether our 2 inputs are the same or different. And then if we look at the left side, it is 1 only in one case, which is 1 plus 1. So that part tells us, are both of our inputs 1? So to make a half adder, we have to answer 2 questions. One is, are our inputs the same or different? And give a binary output. And the other is, are our inputs both 1 or not? And those 2 questions are what are answered in normal computing by these 2 things. They are basically the things that we use to answer those 2 questions. This is the AND gate, and this is the exclusive OR. The exclusive OR works out whether they're the same or different. The AND gate works out whether they're both 1. But we are not, I'm not telling you about classical circuits. Well, I am telling you about classical circuits because I just did. But that is not the point of this exercise. So now we need some other operations. And so the operation that's very important for working out whether they're the same or different, which replicates the exclusive OR in some sense, is this thing called the controlled NOT. So far the only gate you've really seen is X, and X just flips from 0 to 1 and 1 to 0. It's kind of boring. This is the controlled NOT, and what this does is it acts on 2 qubits, and it basically looks at 1 qubit. Well, okay, what does it do? It applies some quantum stuff. But we have to, as humans, come up with some sort of story to explain. So I'm going to tell you the story that everyone uses, but really, it does some quantum stuff. There are other stories that sound completely contradictory, which also explain what a CNOT is doing. But what one usually says is a CNOT involves 2 qubits. We call one of these the control qubit, and we call the other one the target qubit, and it basically looks at the control qubit to see whether it's a 0 or a 1. If it's a 0, the gate itself does nothing. It's as if it wasn't there. If the control qubit is 0, it is as if this CNOT was not even there. If the control qubit was a 1, it is as if you applied an X to the target. So it's like a conditional version of the X. It does an X on the target, which is in this case qubit 1, if the control qubit is in state 1, and if it is in the state 0, else if it's in the state 0, it does nothing. And the end effect of this is to perform an exclusive OR, and we can see this by having it in a circuit. Yeah. Now, why is there not an execution of this anywhere nearby? So let's execute this. Execute QC. We also already have a backend set up. We'll use the default value of shots dot result. Can't type. Dot get counts. So in this specific case, we're getting 1, 1. So let's look at a few cases as to whether we have this X here or not. So in this case, our qubits are initialized 0, 0. Given that this one is initialized to be 0, this CNOT does nothing. We extract outputs, and what do we get at the end? We get 0, 0. Because we initialized it as 0, 0, because the control is in state 0, we effectively do nothing, and then we just extract an output and we get 0, 0. Similarly, let's apply an X to qubit 1. And in this case, we start off 0, 0. And this is still in state 0. This is in state 1. But because this is in state 0, the controlled NOT effectively does nothing. We extract an output. This gives us 0. This gives us 1, which means that the result we get is 1, 0, which is 1 from this qubit and 0 from this one. So again, the CNOT isn't doing anything. So let's now have a case where the CNOT actually does something. So here it starts off 0, 0. We do this to flip this 0 to a 1. And then here the control NOT sees that this is 1. It springs into action by effectively doing another X down here, which means that then when we extract the output, both of them are in state 1. So we see the controlled NOT doing something. And one thing that we can note if we look at different implementations of this is that the output we get on qubit 1 is actually going to be the exclusive OR of the inputs that we give. So if these are 0 and 0, the CNOT does nothing, so this remains 0. If this is 1 and 1, then the controlled NOT flips this 1 into a 0. So in both cases where the inputs here are the same, the output on qubit 1 is 0. But for both cases where the inputs are different, then the output here on qubit 1 is 1. So we get the exclusive OR. We get the same or different information that we need on qubit 1 by just doing a controlled NOT. So the controlled NOT is what we can use to get the same or different information. It tells us whether these two inputs are the same or different. unfortunately, that's not all we're doing at the moment, because it's part of an addition circuit. And as I said, the form that we want at the end is for us to have 2 inputs and 2 outputs, and the outputs are on different qubits than the inputs. So we can't use exactly what we've got here. So what we can instead do is form a circuit of this type. So here we have 2 inputs, we have 2 outputs, and our exclusive OR information is going to be down here. So we're doing 2 controlled NOTs. They're both controlled on the same place. So if you think about what's happening here, if these are both 0, neither of these controlled NOTs do anything. This one remains 0. If these are both 1, then both of these controlled NOTs do something. This does an X to flip the 0 to a 1. This does another X to flip the 1 to a 0. And then hence we got 2 flips and we're back to our initial 0 state. And if these are different, then one of them flips it and the other one doesn't. So we get a 1 here. So our exclusive OR information, our same or different information about the inputs, is now here, and it's provided by these so-called controlled NOTs, which are effectively like conditional versions of the X operation. Now all we need is our next bit of the output, which is going to tell us the other bit, the carry bit of the output, which tells us whether both of our inputs were 1. So how do we do that? Well, we do it using something called a toffoli. So a toffoli, the easiest way to explain it is it's basically like a controlled NOT. So this is a controlled NOT. It does an X here if this is in state 1, but a toffoli does an X here if both of these are in state 1. And then it's basically already doing the thing we want. So in this one particular case where these are both 1, it flips this. Otherwise, it does nothing, and this remains 0. So then, using this, using these X gates just to flip between 0s and 1s, using these controlled NOT gates to get the XOR information, using this to do the job of the NAND, this controlled form of the X, then we have the ability to add numbers. So here is where we encode our input. If we want to add 0 to 0, we don't do any X's here. So 0 plus 0 equals, drum roll, 0. 0 plus 1, which we are encoding by having this as a 0 and flipping this to a 1, gives us the output 1. And now, I know, let's get to the really fun bit. 1 plus 1 is 2. There are only this many kinds of people in the world, those who understand binary, and those who don't. So this is the very basic level of doing something with Qiskit. We're already doing something that we know how to do on normal computers, which is to add binary strings, but it hopefully gets us into the right mindset. It gets us thinking at the right level, which is at the level of these bitwise operations. We have to think how we are going to encode our information in the form of a binary string. Then we encode that information. Then we have to think of how we are going to manipulate our information in the form of binary. And in this case, we've done it in a way which is exactly the same as how a normal computer does it. So we will get no advantage over normal computation doing this. But in general, in quantum computing, we take more complicated problems and we try and do them in a way that is better. So we can get an output faster than we would on a normal computation. So this is the first of the notebooks that I was going through today, and so far we have just looked at qubits being bits. So we've completely demystified these qubits. Hopefully, we've taken all of the magic out of qubits. We've just used them as bits. So now we can start looking at some of what. Yeah. Mm-hmm. Okay. Yeah. Yeah. So I'll deal more with an H-gate in this notebook. But yeah, that's an important point about the C0. I told you earlier that the measurement was this point where you extract an output from a qubit, and it's the most important point in a qubit's life that it has this measurement. And then I was talking about the qubit, the C0, the controlled knot, and I was talking about it in this way that we usually do, that the C0 looks at a qubit and based on the state does something. Now what does it mean for a C0 to look at a qubit? Well, now we're getting into philosophy. It means a different thing for us to look at it. It means a different thing from us doing a measurement to determine its state, and then based on the result of that measurement doing an X. That would be called a classically controlled X, and it is different. So a C0, so a C0 can work even when the state of a qubit is not deterministic. So even when there is some randomness as to the 0 or 1 state of the qubit, the C0 also works, and it serves to basically spread out that randomness. So if you have one qubit and it's randomly in state 0 or 1, and you do a C0 controlled on that, you'll get 2 qubits that are randomly in state 0, 0 or 1, 1. Although this randomness is not the normal kind of randomness that we usually experience, it's kind of the tip of an iceberg, and I'm going to try and explain the randomness inside a qubit, including the H-gate, in this next notebook. And in this notebook, this notebook is made so it can run on a pew-pew, just because that's more fun than not running it on a pew-pew. I'm not actually going to run. Oh, it's already there. I'm not actually going to run it on a pew-pew here. So if you don't know what a pew-pew is, there was one in very large form on the screen in the keynote this morning. But it's this. It's a microprocessor based, microcontroller based games console. It's got an 8x8 pixel screen. It's got some buttons, and you can use Python to make games for it. It's a great fun way of using Python to do something. It's a great way of teaching people how to use Python. So I decided to get a quantum simulator running on this microcontroller so that people could easily make quantum games. And also it helps sort of visualize what's going on here. So instead of using histograms, I'm gonna pretend that we've got a pew-pew up on the big screen here. So let's see if that works. And my emulator uses matplotlib, because how better to emulate a games console than using matplotlib, eh? Right. Let's try and get this to actually fit on the screen. Okay, I think it is fitting on the screen. It just goes big when it stops running. Oh no, maybe not. Okay. I'll have to flip between the between the different screens for the controller and the screen. So this is a pew-pew, and I've set in this program I've set all of the pixels to a kind of dim value, except for that one over there, which is bright. And we're going to be using actually that pixel down there to display the output of a qubit, and we're going to use the controllers to manipulate this qubit. So, well, I won't go through how pew-pews work because we don't have that much time. But here is I'm using a qubit initially, and it is initially in state 0. And I'm going to represent the binary output of this qubit as the brightness of that pixel down there. So if I press up on my gamepad. Come on, work. If I press up, nothing works. Okay, change of plan. That would be the funnest way to do it if it worked, but let's not spend too long making it work on this big screen. It is a tiny bit flaky. So instead, we'll go through this notebook, and I'm just going to do it statically. This is from the web. So the important thing about qubits is that they are quantum objects, and as quantum objects, they obey Heisenberg's uncertainty principle. So here we go with the last portion of this workshop, which is a lecture in quantum mechanics, and we begin with Heisenberg's uncertainty principle. So if you've ever heard about quantum, you might have heard about this notion of the uncertainty principle, which means that for a quantum object, for example, you cannot precisely know both its position and its momentum. If you know its position with absolute precision, then its momentum is completely uncertain. And if you know its momentum with absolute precision, then its position is completely uncertain. It's randomly anywhere in the universe. So quantum qubits are quantum objects, and they obey this uncertainty principle, but I don't have position and momentum. The only quantities related to a qubit are binary outputs. It gives you zeros and ones. So the way that we get the uncertainty principle with qubits is by noting that this operation that we've been performing, this measure operation, is not the only way of extracting an output from a qubit. So it is a way of extracting an output from a qubit, is a way of inducing a qubit to tell us whether it is a 0 or a 1, but it's not the only way. And if you go to our cloud-based service and you use the GUI there, instead of on our matplotlib we're visualizing things, it looks like, now, even though I've given up on this, it's still running in the background, and it's causing my fan to start going a little bit mad. So I'll just shut that down a moment. The symbol is this, so it's the same except it has this Z here. So the reason for this Z, if you look on this version, is a hint that it's not the only way to extract an output. So this is one way to extract an output, but there is also another way, and the other way is called, so the normal way, which you get by just doing a measure gate, is called a Z measurement. So this way of extracting an output is called a Z measurement. This alternative way is called an X measurement. So you can implement it like this by just doing an H, whatever that is. I haven't yet explained that, and then a measure. Now, why does this work? Well, it does. And to be honest, if I had more power in Qiskit, there wouldn't be a measure operation. It would be measure underscore Z or something like that. So you're explicitly saying it's a Z measurement. And you would do this by using measure underscore X. But I don't, so we're stuck with it. The physics of the device means that one of these types of measurements is very easy to actually do, actually implement. So with our actual qubits, we always extract a measurement using a Z measurement, and we have to kind of use hacky ways to do the other measurements. But in terms of the theory behind qubits, this is a distinct way of extracting a measurement, extracting an output, sorry. So this is another way we can extract an output from a qubit. And so there's different ways we can extract an output, but the important thing about a qubit is it can only store a bit of information. So you can't use these two ways of getting an output to extract two different bits. You can't fool it into storing more information than it really can. It can only store a bit's worth of information. So to see this, let's create a circuit QC0, which is just an empty circuit. Let's then do an X measurement of this circuit and run it. And what does it give us? Well, we've been doing this the whole session so far. If you take a qubit and you straight away extract an output, it will give you a 0. So this gives us 0 the whole time. But if we instead of extracting this output using the Z measurement, if we instead extract it using the X measurement and we look at the output, then it will randomly be either 0 or 1. So this is an important principle of qubits. Unlike bits, which are 0 or 1, and there's only one way to ask a qubit. Sorry, there's only one way to ask a bit whether it's 0 or 1, and that's just to look at whether it's 0 or 1. But with a qubit, there's different ways to extract the output. If you prepare something which is definitely going to give you 0 for a Z measurement, which is what we had here, and you instead do an X measurement, the result is completely random. So you're getting a random output for the X measurement, even though the result would have been definite for a Z measurement. I know this is a little bit abstract, but this is a quantum computing session, so it does have to come in at some point. Now we can try doing this H-gate, which I've kind of introduced a little bit before, but we've not really looked too much at it. So if I take a circuit and I make it an empty circuit, and the only thing I do to it is an H-gate, we can look at what effect that has. So now let's extract an output just from that. And we've got two ways of extracting an output. So one of those ways is to do a Z measurement, which is our normal way of extracting an output, and we get a random result. So what is this H-gate? Is it like a coin flip, which just makes stuff random? Well, no, because if we instead take that same circuit and do an X measurement, then we get a definite result. It always comes out 0. So what the H has effectively done is just moved the certainty. We had a qubit which was very certain about the output it would give for a Z measurement, and we made it instead very certain about the output it would give for an X measurement, and the other one is always random. So these are two different ways of extracting an output, and they can't simultaneously be certain about what they're going to give, but we can move the certainty around between them. One of them can be certain, the other one not. We can also look at other gates. So there's something called a Y rotation, which you can do by doing RY. You can specify the qubit that you're acting on, and then you put in an angle in radians, which I'm just putting minus pi by 4. And for this particular example, if I take now this circuit and I measure it in use a Z measurement of that, then what the output I get is 87% of the time it comes out 0, and 13% of the time it comes out 1. So it's mostly certain that it's going to be a 1, but not entirely certain. If we instead do an X measurement, in this case it's mostly certain it's going to be a 1. It's not entirely certain. So we can also kind of share out this certainty between it, but the certainty that a qubit holds is a conserved quantity. It can only have so much certainty. And we can either make the output of a Z measurement certain, or we can make the output of an X measurement certain, or we can have a compromise between the two, but there is a conserved amount of certainty in there. So that is basically why one way in which qubits are different from normal bits. And usually this will be explained in terms of superposition. I don't really like the term superposition because it refers to what's going on in the mathematics, in the linear algebra. So if you want to get into the linear algebra, then you'll see a superposition. But if we do it without the linear algebra, we just look at the behavior of a qubit. It's like this. We have multiple ways of extracting outputs, and we have a conserved amount of certainty. And basically, making quantum algorithms is about moving this certainty around in certain ways that we get our input that we've encoded in there, and it's certain about our input, and then moving it around in certain ways to get our output. And this is a completely different approach to creating algorithms than we usually have in normal computing. So I've just been told that we're coming to the end. How long do I have? 5 minutes. Okay, so I can't explain 50 years of progress in theoretical physics in 5 minutes. 10 minutes maybe I could have done it. But, yeah, okay, 10 minutes I could. Well, 10 minutes, I say 10 minutes maybe I could have done it to make myself seem like a great teacher, but maybe 10 minutes is also a little bit. But basically, yeah, if we use the controlled not, let's go back to somewhere we can actually execute code. So now let's do a 2-qubit circuit, quantum circuit, 2-2, and then we do a Hadamard for this H gate, and then we do a controlled not, and well, I've just done the ASCII version there rather than the matplotlib, so it doesn't look quite as nice. But what is this going to output? So this is, if we think about it in terms of outputs for Z measurements, then this is randomly either 0 or 1. So this is going to, if it sees a random 0, it will do nothing here and keep this 0. If it sees a 1, it will flip this to a 1. So what we would then expect, and I can't be bothered to write out the execute command, so let's just steal it from somewhere else. Oh, I will need to put measurement gates in, of course. If we put some measurement gates in here, qc.measure, so I'm just going to put some Z measurements in. qc.measure. And then I run that. Then it gives us what I just predicted. It's either randomly 0, 0 or 1, 1. So it's created something which is random but also correlated. If we instead were to do X measurements here, which we can do by just having qc.h 0 and qc.h 1, well, I'll start that from the beginning. So in this case, so before I was taking this circuit and doing Z outputs, and it gave me randomly either 0, 0 or 1, 1. Here I do X output, I use X measurements instead, I extract the output in this other way. It also gives me randomly 0, 0 or 1, 1. And it's kind of weird. So one thing that's telling us is, if you look at each qubit individually, it doesn't matter if you're using a Z measurement or an X measurement, it's giving you a random result. And the reason for this is, now again, it's certainty. There's a certain amount of certainty contained within qubits, and by using operations we move that certainty around. It started off that they were both certain that if you did a Z measurement you would get the output 0, and now we find that if we do Z measurements of both or X measurements of both, in both cases it's correlated. So here we have a certainty that the outputs are going to be the same. The outputs themselves are random, but we have the certainty that they're going to be the same. So we have instead made ourselves certain about certain factors of the combination of the two qubits instead of the qubits on their own. So if we start using controlled knots when we don't have certainty on each of the qubits, then we run into these interesting effects. And actually these effects have things that are beyond what any normal variables in normal computers can do. So if you look in that section of the Qiskit textbook, there's an example, because you might think, well, a qubit is like a bit, but from what I've told you about a qubit, it's kind of like a bit but with a random number generator attached. You could probably very easily write something that reproduces the kind of properties of qubits that I've told you about today. And it tempts you to think that maybe qubits are just equivalent to some pile of bits, just like dicts are, or lists are, or ints are, or anything are. But qubits are a type of variable that are fundamentally different from any kind of variable that we have in normal computers. And it's when we start getting a little bit more involved into how information moves around inside these things that we can start seeing now. So I'll have to refer you to that to look into afterwards, because we don't have enough time for it now. So one thing I will just touch upon before I stop is if you want to do something interesting with a qubit, with quantum computing, then to do something that a normal computer can't, you need about 50 qubits, and you need maybe a fancy algorithm. If you want to do something interesting, fun, then 1 qubit is enough. So if you experiment with 1 qubit, then with that you can do some. I've got a suggestion for some procedural generation that you can do. So if you want to look into that afterwards, as your first example of doing something in Qiskit, then that's something you only need 1 qubit. You don't need any physics knowledge, but you can do something that's kind of fun. And in fact, this last weekend was Ludum Dare, which is a game jam. So if I made a game for that game jam, which was based on my procedural generation project. So as my final thing, I'm gonna make that run. So it's a game. The theme for the game jam was start with nothing. So it's procedural generation, which initially has no seed. So you create the world as you move around on it. And the procedural generation for this, it's very simple, but it was done using Qiskit, using just 1 qubit. So this is the kind of thing you can do with only 1 qubit. It's not gonna cure cancer, but it might be fun. And then that can be a first step if you want to start looking at the kind of things that you might be able to do with Qiskit over the next decade, and also when the revolution comes. So that's basically all I've got to tell you. Thank you for listening. Any questions? What the? Yeah? So, let me think. Well, yes. Yes is the answer. I think the gates that I had were a universal gate set, which means that they could on their own do everything, but there are much more gates. And in fact, maybe one thing to leave you with is I have this sort of gamified and Jupyter Notebook-based game that you can use to get an introduction to all of the gates, and it's called Hello Quantum. So if you go to ibm.biz/helloquantum, then that's a way of finding out more about all of the gates. But yeah, there are more, but they take that same sort of general form. Any more? Okay. Well, hopefully you are motivated to look into some of the other resources that I provided, and thank you for coming.